There's a virus that pretty much all of us carry, an invisible companion that for some people can turn into a really serious enemy. For decades, it's just been this silent threat. But what if we could finally stop it in its tracks? Well, we're about to dive into a major scientific breakthrough that's aiming to do exactly that.
Just look at this number for a second. 95%. Let that sink in. That's the estimated percentage of people all over the world who are infected with a virus you might not have even heard of, the Epstein-Barr virus. It's, without a doubt, one of the most successful viruses on the entire planet.
And this is it. This is the Epstein-Barr virus, or EBV for short. Now, for most of us, it's basically a harmless passenger just hanging out dormant in our bodies for our whole lives. But for an unlucky few, it can wake up and become a trigger for some really serious conditions, everything from multiple cancers to chronic diseases. It's a silent threat, hiding in plain sight inside almost all of us.
All right, so let's take a closer look at this invisible enemy. What exactly is the Epstein-Barr virus, and how on earth did it become one of the most common infections in the world?
So yeah, EBV is way more than just some common bug. It actually belongs to the herpes virus family, and that group is famous for its ability to just lie dormant in our cells for years, sometimes decades. This latency, well, that's its secret weapon. It can just reactivate later in life, and that's when it can potentially trigger these severe health problems. It's a hidden risk factor that the huge majority of us are carrying around every single day.
So that begs the question, right? If this virus is so common and so potentially dangerous, why haven't we stopped it? Well, the answer is that EBV is an incredibly formidable foe.
This quote from Dr. Andrew McGuire at the Fred Hutch Cancer Center, it just nails the problem. EBV doesn't just infect a cell here or there. Oh no, it has a master key to our B cells, and those are the very cells that are supposed to create antibodies to fight infections. It's a widespread brute force invasion that has made finding an effective defense just unbelievably difficult. And if that wasn't hard enough, there's another huge problem. When scientists have tried creating treatments using antibodies from, say, mice, our bodies often see the treatment itself as a foreign invader and just attack it. It's like your own defense system sinking the rescue boat that's coming to save you.
But now, things are changing. There's a new shield. Researchers at Fred Hutch have pioneered a totally new strategy, a breakthrough that might finally give us the upper hand against this tough virus.
Okay, so what they did here is just so clever. Instead of using those traditional methods, the scientists used mice that were specially engineered to produce fully human antibodies. The proteins our bodies use to tag and destroy invaders. This completely bypasses that rejection problem. These mice basically became tiny factories for creating powerful antibodies that could target the exact tools EBV uses to break into our cells.
Now, to really get how this new therapy works, you got to understand EBV's two-step invasion plan. Think of it like a grappling hook and a key. First, a protein called GP350 acts like the hook, latching the virus right onto our B cells. But just latching on isn't enough to get inside. It needs a key. And that's the job of a second protein, GP42, which literally unlocks the cell door and lets the virus waltz right in.
And this is where it gets really cool. The researchers basically asked, what's the better strategy here, blocking the hook or blocking the key? The results couldn't have been clearer. An antibody targeting the hook, GP350, only offered partial protection, but an antibody targeting that entry key, GP42, it offered complete prevention of infection. In lab models, the virus was stopped cold. They had found the kill switch. I mean, this is amazing science, right? But what's the real-world impact? What does it mean for people? Well, the most immediate impact of this discovery could be for a group of very, very vulnerable patients, those who have received organ transplants.
In the US alone, we're talking about over 128,000 people getting an organ or bone marrow transplant every single year. And for these patients, EBV isn't just some tiny risk in the background. It is a potential life or death complication.
And here's why. It's all because of this really dangerous condition called PTLD. You see, transplant patients have to take drugs that suppress their immune systems. It's necessary to stop them from rejecting the new organ. But that also means a dormant EBV infection can reactivate and just run wild. This can lead to PTLD, which is a life-threatening form of cancer. The consequences can be devastating.
And listen to this quote from Dr. Rachel Bender-Ignacio. It really drives home how urgent this is. Viremia is just a fancy word for the virus actively circulating in the blood. And as she points out, preventing this is a huge unmet need. Right now, there are no targeted therapies for this.
So a treatment that could stop EBV before it even starts would be an absolute game changer in transplant medicine.
You see, their risk is like a perfect storm of factors. First, the drugs they need to survive weaken their defenses against the virus. Second, the new organ itself can sometimes carry the dormant virus right into their body. And third, children, who might have never been exposed to EBV before, are especially defenseless against a brand new infection right after a transplant.
Okay, so we've got this incredible discovery. We know who needs it most. So what's next? What's the path from the lab to the patients who are waiting for it?
The endgame here is a preventative therapy. Just imagine a simple infusion of these powerful antibodies, given to transplant patients and other high-risk people. It would act as a temporary but incredibly powerful shield, blocking the virus before it ever gets a chance to cause any harm.
And there's actually a pretty clear roadmap to get this done. The discovery and the intellectual property are locked in. The very next crucial step is finding an industry partner to start making the therapy on a much larger scale. After that, it'll move into safety testing, before finally starting clinical trials with the actual transplant patients who could benefit the most.
And, to bring it back to Dr. McGuire one last time, there is real momentum here. After so many years of frustration in the fight against EBV, this discovery is a huge leap forward, not just for science, but for the thousands of patients whose lives it could one day save.
Think about it. For thousands of years, this virus has lived inside of us, our silent and sometimes deadly companion. And now, we may have finally found the key to disarming it. It really makes you wonder, what other ancient viral enemies could this new shield help us conquer next?